Now that we have understood that the behavior of the queue both at the input and at the output of a router depends upon what algorithms are being used. For that, we shall explore what are the potential queue management strategies. In this module, we shall understand what do we mean by active queue management. Then we'd look at the baseline algorithm called the drop tail, and then we'll go into the details of random early detection algorithm. The classical reference I've chosen for this module is by Sally Floyd and Van Jacobson, Random Early Detection Gateways for Congestion Avoidance. Let's look at drop tail first. Drop tail is, as the name implies, drop the tail. It is a conventional algorithm that handles the packets which arrive at the input queue when the queue is already full. A router tries to buffer as many packets as possible, but which it cannot buffer, it just drops them. Tail drop seems natural and intuitive. However, it treats the queue and the incoming packets belonging to different traffic flows unfairly. Active queue management, as the name implies, is a more proactive approach when a router buffer starts to realize that it is approaching its upper limit. Active queue management is not a blindfolded or dumb packet dropping algorithms. Rather, it is an intelligent form of packet dropping mechanism in which the packets are dropped at the input of a buffer depending upon some objective function to be achieved. Of course, the overall goal is to reduce the overall network congestion. Random early detection is a kind of active queue management strategy. If we consider the name, it drops the packets randomly, but it preempts that the buffer is going to overflow very soon. So that is why it is called early detection. RED is implemented by monitoring the average queue size, and it drops the packets based on the probabilities. These probabilities are assigned on the basis of the objective function and the overall goal of reducing the network congestion. If the buffer is initially empty, then all the incoming packets are enqueued and no dropping is exercised. But as the queue grows, there is a linear function of probability that is dropping the packets. This queue will start to approach its upper limit, so the probability would also increase that a packet should get dropped. Which packet is to be dropped is a random phenomenon. Of course, when the buffer becomes full, the probability of packet drop becomes 100%. That is, if the buffer is becoming full, any incoming packet has to be dropped. Figuratively, we can establish a relationship between the average queue size and the probability of dropping the incoming packets. Queue, which is handling the packet drop using the RED mechanism, can be best described using a linear relationship. This linear relationship is bounded by the minimum threshold, that is, RED is going to be activated when the buffer occupancy reaches a lower threshold, and then the probability of packet drop increases linearly, and it goes up to a maximum threshold. After the maximum threshold is reached, it means the buffer is now in a state of complete overflow, and there the probability of packet drop immediately becomes or overshoots to 1. Within this figure, you can see that the inset shows the average buffer occupancy, that is the average length, which fluctuates between the minimum threshold and the maximum threshold. Using these relationships, we ensure that some kind of congestion control mechanism using the queue management is in place.